Okay, so welcome to ours. I'll just give you some, before I introduce Tony, I'll just give you a brief rundown of how these meetings work if you haven't been here before. So these meetings are recorded, and if you ask a question during the talk, you will be recorded, and also if you ask a question after the talk. But at a certain point after the talk, we'll turn the video off and there'll be a free discussion following the talk. Next, the security settings are that the chat is disabled for chatting to everybody, but you can always send me a message. For example, if you see something weird happening or somebody's abusing the system, then you can just let me know and I'll try and deal with it. Third of all, we do encourage questions. So during the talk, if you would like to ask a question, either write to me in chat or put your hand up using the Zoom put your hand up functionality. And finally, we ask everybody to keep your cameras on if possible. It just makes a nice atmosphere for everybody that you can see other people around. But without further ado, I think we'll start the talk. So it's my pleasure to welcome Antonin Kucera, who'll tell us about efficient analysis of VASS termination complexity.
Okay, so it's my turn now. Hello, okay.
Yes, go ahead.
So, first of all, let me thank you for inviting me. It is really very nice to see all of you again, at least virtually. So this talk is a kind of survey talk about the results about VASS termination complexity that have been achieved mostly in the last 2 years. And what I'm presenting here is mostly a joint work with these nice people listed here. So what is a VASS? Well, this is the standard thing. So we have essentially a finite state program operating over a bunch of unbounded integer variables, which can hold only non-negative values. So this is a simple example of a VASS, which doesn't do anything particularly interesting. It has 3 control states and transitions, and each transition is equipped with a vector of counter updates. So when, for example, this transition is executed, the first counter remains unchanged, while the second counter is increased by 5. And since the counter cannot hold negative values, it may happen that some of the transitions are disabled in certain configurations when there are not enough tokens in the counters. So for example, this transition requires to have at least 6 tokens in the second counter. So if the second counter holds currently 3, this transition is disabled. So what we are interested in this talk is VASS termination complexity. So let me define what that is, and then I try to convince you that this is interesting enough to be studied. So first, for every configuration, PV, so P is the initial control state and V is the vector of initial counter values, we can consider the maximal computation initiated in the configuration, so a computation which cannot be prolonged. And we can consider the maximal length of such a computation. Of course, in principle, it can be infinite because it may happen that the maximal computation initiated in a given configuration is actually infinite. So the termination complexity is a function which to every integer n assigns the length of a maximal computation initiated in a configuration where all counters are initially bounded by the n. So since increasing the initial counter value can only prolong the computation, there is this well-known monotonicity in VASS computations, it would be equivalent to say that we start with the counter initialized to the n. So it would not change the definition, but we keep it like that. And the problem we consider is the problem of analyzing the asymptotic growth of this function of this termination complexity. So how much time it takes for a given VASS program to terminate. So why is this interesting? So the motivation for studying this problem comes from program analysis. So here's a simple example. So VASS are particularly apt for modeling programs with integer variables, and they are also used to model parameterized systems. So here we have a simple program with the following skeleton. So the execution of the program is governed by 2 variables, I and j. So first we ask what is the initial value of I, And then we execute this cycle, which as long as the value remains positive, decrements the value. Then we assign the current value of I to the j, and then we execute the internal while loop, which is executed as long as the j is positive, and the j is decremented within the cycle. So we cannot model this program directly with the VASS because of two reasons. So first, a VASS cannot test a counter for 0 explicitly, so that's the first obstacle. And the second obstacle is this assignment. This is what we cannot model directly because there is no instruction for assigning one counter to the current value of the other counter. But there is a way to overcome this, so we can transform this program into an equivalent program where this assignment is modeled in the following way. So we introduce an auxiliary variable, and we initialize this j and aux to 0. And this inner cycle is basically responsible for transferring the content of the I counter to the counter j and aux. So we keep decrementing the I as long as it stays positive and incrementing j and aux. So this, in fact, means that we assign the variable j and aux the current value of I by this while loop. So we basically achieve the situation when the j holds the value of I. This is okay. But then we also need to restore the value of I back because this is currently 0. So what we do, we transfer the tokens from aux to I. This is the purpose of this inner loop. And then we continue by executing this loop again. So this program is essentially equivalent to the original one, except that the computation of this program is longer because instead of executing just one instruction, we execute 2 cycles which emulate this instruction. But anyway, any bounds, any upper bounds on the running time of this program are also valid for this program. And the reason why we did it like that is that now it is possible to model the execution of this program by a VASS with 3 counters, which hold the current value of I, j, and aux. So we start in this configuration. We proceed by simulating this instruction, which decrements the first counter, this I. So this is this vector. And then we set both of these variables to 0, and the VASS can achieve that by decrementing the second and the third counter by 1. Of course, we cannot enforce that. It is also possible that the VASS decides to move along the transition before the j and aux are actually emptied. This is what we cannot influence, but still the VASS can simulate the computation of the original program. So it over approximates the behavior of the programming calls. So then when we are done with this, we proceed by simulating this while loop. This is where we decrement I and increment j and aux. And then we proceed to this cycle. This is where we transfer the tokens from the last counter to the first counter again. So this is the effect of this while loop. And then we finally simulate this while loop where we just decrement the counter j. And when we are done with that, we proceed by restarting the computation from this instruction again. So this is a VASS model of this program. And now, if you look at this VASS, you may, after some analysis, observe that the termination complexity of this VASS is quadratic. So this VASS terminates after O(n) squared steps. So this is bound, which is valid for this program, and hence also for this program. And if you look at this program again, you may observe that this bound is actually asymptotically optimal. So despite the fact this is just an over approximation of the original program, we obtain a bound which is at least asymptotically optimal. So now, what are the very basic questions about termination complexity? So obviously the first question is whether the termination complexity is well defined, whether the VASS terminates for all possible inputs. That is, whether this L of n is finite for every n. So can we decide this? Yes, very easily, because the existence of an infinite computation is actually equivalent to the existence of a self-covering computation of this form. So we go from PV to PU, where this U is in every component only larger than this V. So obviously, if there is such a computation, then this can be pumped. So there is an infinite computation, and this is also necessary. The existence of such a path is a sufficient and necessary condition for the existence of an infinite path, of an infinite computation. And the existence of such a path can be decided in polynomial time by using Kucera-Sullivan algorithm. So this is simple, and yes, this problem is thus solvable in polynomial time. The second very natural question is, okay, so suppose that this Ln is finite for every n, but how fast it can grow? Well, again, we can give a good answer to that question, but to formulate this answer, we need to introduce the hierarchy of fast-growing functions. So what I have in here is almost the standard hierarchy of fast-growing functions, except that the first three elements are defined somewhat differently so that the definition better suits purposes of this talk. So the first function in our hierarchy is the linear function, the second one is the quadratic function, and the third one is a single exponential function. And then the rest is standard. So the next function is defined as a composition of the previous function n times, and then the function is applied to the n. And on top of that, we also introduce the corresponding class gk, which consists of all functions which are bounded by a finite composition of the function fk. So this mu has to be a constant. Now, the reason why we use the G letter is that this corresponds to this class gk corresponds to the kth class in the standard Grzegorczyk hierarchy, in the sense that it captures the growth of the functions in the corresponding level of the Grzegorczyk hierarchy. So we also call it Grzegorczyk class, this gk. So now, how fast can Ln grow? Well, we can show that for every k, there exists a terminating VASS such that its termination complexity is larger than fk. So it can really grow very, very fast. I mean, examples, the construction of this VASS is essentially due to the old paper by Meyer and Meyer, published in 1981. On the other hand, we can also show that for every terminating VASS, which has d counters, we have that the termination complexity belongs to this class g d plus 1. It cannot be larger. It cannot grow faster than that. This follows from the results of Sylvain-Schmidt's established 2 years ago. Okay, so these were the very basic questions. So what else is known about termination complexity? Well, this is pretty much everything what is known at the moment. So first of all, the problem whether the termination complexity is linear is solvable in polynomial time. And there is a kind of gap theorem telling you that if the termination complexity is not linear, then it is at least quadratic. So for example, it cannot happen that the complexity is something like n log n or something like that. It cannot be. Then the question whether the termination complexity is polynomial, so whether there exists a k such that this L is O n to the k, this is also solvable in polynomial time. And furthermore, there is again a kind of gap theorem. If the termination complexity is not polynomial, then it is at least singly exponential. This was proven by Jean Leroux 2 years ago. So there is sort of a refinement to this result recently proven by Florian Zolleger, which says that for every given k, the problem whether the termination complexity is O n to the k is decidable in polynomial time. This result actually holds only for strongly connected VASS. We have some recent results established together with my students showing that for general VASS, which are not necessarily strongly connected, this problem is apparently, if we are not mistaken, could be complete. And finally, there is a result saying that for every k, the question whether the termination complexity belongs to the class gk is also solvable in polynomial time. And again, there is a kind of gap telling you that if the complexity does not belong to the class gk plus 1, then it grows at least as fast as the generator of the next class, or this class jk plus 1. So at least as fast as the function fk plus 1. So this is pretty much everything what is known These
can I ask a question, Tony?
Sure, yeah, go ahead.
Given that VASS is essentially the same thing as Petrinet, I guess all of these things can be translated into the language of Petrinet, right?
Yes, I mean, in one way.
So essentially, for example, these gap theorems, one cannot have a Petrinet whose termination complexity is n log n. Or is there something more?
Most likely, only that. First of all, we would have to agree on precise technical definitions. So,
sure.
What do you mean by that? But okay, intuitively, it should be the case. Yeah.
Okay, thanks.
Okay, I mean, we can also have other questions. So, if anybody is interested to throw a question at the moment, I will be happy.
Yes, absolutely. So you need to go through me. So I'm the gatekeeper.
Okay. Okay, good. Okay, so I go on. So I mean, I should also tell you that the techniques used to establish these results are diverse. I mean, this is not just a single technique which would capture all these results. And I can also say that these results are actually non-trivial. I mean, this is not easy to obtain these things. So I cannot tell you how is all this proven. I'm not going to sketch all the details. I will just concentrate on the first case because it is relatively simple and intuitive. And when I'm done with that, I continue with more general models where we extend VASS with stochastic states and also with angelic non-determinism. So we will have a VASS game. Okay, so back to this linearity. So what I would like to do now, I would like to sketch the argument which is used to prove that the problem whether the termination complexity is linear for a given VASS is solvable in polynomial time. And I also try to sketch the argument why it is the case that if it is not linear, then it is at least quadratic. We will need just one auxiliary notion for that, which is the notion of a simple cycle. So a cycle in the graph of a given VASS is simple if it does not visit the same control state more than once. And the effect of such a simple cycle is called an increment. Maybe the word increment is not very suggestive in this context, but anyway, we use it. So since there are only finitely many simple cycles, there are only finitely many increments, the corresponding vectors of counter changes. And we can, for the moment, imagine that we have this set in hand. I should say that this set inc of all increments is computable in time, which is exponential only in the dimension of a given VASS. So in the end, since we want to obtain a polynomial time algorithm, we will not be computing the set inc at all. We will overcome this. But anyway, this set is very useful to illustrate the underlying principle of the argument. And this is actually shown in here. So here we have 3 examples of a 2-dimensional VASS. So these examples actually sort of represent the 3 cases, the 3 possible cases that can happen. So let's have a look at the first VASS first, and let us classify or identify all simple cycles. There are actually 3 of them. This one, its effect is -1, 1, so this is an increment. Then there is the second cycle. This effect is -1, -1, so this is this guy. And there is a third simple cycle, this one. Its effect is 1, -2. So now if we draw these increments as vectors, we may observe that it is possible to fit all of these increments, all of these vectors, into an open half space determined by the normal, which is strictly positive in every component. And the existence of such a normal and such an open half space is obviously sufficient for the linearity. Why is that? Well, if you have a computation, then you can decompose this computation in a simple cycles. And if you have a computation of length n, there will be like omega n simple cycles. So about n simple cycles. And each of them moves you in the direction opposite to this normal by some fixed amount. So it moves you towards the axis by some small amount bounded away from 0. So obviously you need about n such cycles to reach one of the axes, and this is where the computation inevitably stops. So again, the existence of such a normal, which is positive in every component, and the open half space, which contains all increments, is sufficient for the termination complexity to be linear. This was the first observation. Now, it is also possible that no such open half space exists. And this is shown here in this example. So here we have slightly different increments because we have changed the effect of this transition. It is no longer 1, -1, but it is 0, 0. So now we have 3 increments like that. So if we draw them, we obtain the following picture. So now the only way how to close these 3 vectors in a half space is to choose the hyperplane so that it goes through these 2 vectors. The associated normal vector has to be orthogonal to this line. But still, this is not contained in the open half space determined by this normal, but in the closed one. So what can we do now in this case? Well, observe that these 2 vectors are pointing in the opposite direction. So what you can do, if you start at some point, which is somewhere deep in the first quadrant, you can go down using this simple cycle. So imagine that you have a point starting here. You go down to the axis until you cannot go any further. And then you basically switch by performing this transition to the other cycle, which allows you to go up again along this diagonal in the direction of this vector. So basically you go down as long as you can, then you have to perform this switch, but here you lose 1 token in the y in the second component. So you go like in this direction again, then you go up, you go down as long as you can, then you have to go down again, and so on. And thus you produce a kind of zigzag or a snake, if you wish, whose length is quadratic in the number of tokens stored in the original configuration. So if you start with in a point in here where both counters hold the value n, the length of this snake we just produced will be quadratic. And this holds again sort of generally, because if you have high dimension, more increments, it is not necessarily the case that you have a pair of 2 increments which point in the opposite direction, but what you can always do is that you produce such vectors as a combination of some of these increments. And as soon as you have such a combination, you can play sort of the game I have already indicated. So you produce a zigzag or a snake of a quadratic length. So this is the way how you prove the other part of the theorem, which says that if the termination complexity is not linear, it is quadratic. So there is also a possibility that these increments cannot be hidden in a half space at all, like in this case. But this is precisely the case where this VASS does not terminate, because you can go arbitrarily far in the first quadrant just using these 2 simple cycles by combining them. So this is the essence of the argument. So this is formatted precisely here. So we have a d-dimensional VASS, and the theorem says, okay, if there is an open half space determined by a normal which is positive in every component, and all increments are hidden in this open half space, then the termination function is linear, otherwise it is at least quadratic. So how could we use this to decide the linearity? Well, a naive way would be compute the set of all increments and then use a simple linear program to decide the existence of the corresponding normal. The only problem is that this would yield an algorithm which is exponential in the dimension. So in fact, in the paper, we avoid this. We encode the problem somewhat differently by a different linear program, and thus we avoid the computation of the set of increments. And this will result in a polynomial time algorithm. So there's one more thing worth to mention. So in a program analysis, a popular way how to prove the termination of some program, or even a fast termination of some program, is to use ranking functions. And the ranking function is a function which intuitively has a tendency to decrease along the computation. And the results established about ranking functions typically say, if there is a ranking function with certain properties, then the program terminates fast, something like that. So it is like a sufficient condition which guarantees termination or fast termination. In our case, this is somewhat better. First of all, the ranking functions can be constructed in a very simple way, and moreover, their existence is not only sufficient but also necessary for linear termination. So let me make this more precise. So what is a weighted linear map? Well, a weighted linear map is a function which to every configuration, PV, assigns a sum where the first summand is a weighted sum of the counter values. So this C is a vector of weights, and plus this is the weight of the control state. So this is a simple mapping like that. And we say that such a weighted linear map is a weighted linear function if for every configuration PV and every transition we have that the value of this weighted linear map decreases at least by some epsilon. So this is some fixed constant. So clearly, the existence of such a weighted linear ranking function is again sufficient for linear termination, but we can prove that it is also necessary. And in fact, we can compute the weighted linear ranking function for a given VASS if it exists. So in the case of VASS and linear termination, the existence of such a weighted linear ranking function is both sufficient and necessary condition. So we obtain a method, a proof method, which is both sound and complete. Okay. So now let's move to richer models. So now we will have VASS MDPs, where the set of control states also contains some control states which are stochastic. So the successor in stochastic or probabilistic control states is determined randomly. So a part of the vectors of counter changes, there are also positive integer weights assigning to these transitions. And when we compute the probability of executing a given transition in a configuration with control state R, what we do, we have a look at all transitions which are enabled in the configuration and then normalize these weights into probabilities. So for example, if we are in a configuration where only these two guys are enabled, then the sum is 7. So the probability of executing this edge will be 2/7, while the probability of executing this edge will be 5/7. If we are in another configuration where all of these transitions are enabled, then the sum is 10. So the probability of executing this transition will be 5/10, which is 1/2. So this is the model. So now we can also consider the concept of termination complexity, only that now we must define it a little bit differently. So for every configuration, every initial configuration PV, we consider its termination value, which is obtained as a supremum taken over all strategies. The strategy is a recipe how to resolve the choice in a non-deterministic state. So here we consider strategies which are history dependent, so original type of strategies. And as soon as we fix a strategy and apply it to the VASS, we obtain a Markov chain. And in this Markov chain, we can consider the expected length of a terminating computation. So the termination value is the sup taken over all strategies for resolving the non-deterministic choice of these expected length of a terminating computation. And then we can define the termination complexity pretty much the same way as before. So to a given n, we assign the maximal termination value of a configuration where all counters are bounded by the n. So what is known about these VASS MDPs? Well, actually not much. There is only one result, which says that the problem whether the termination complexity of a given VASS MDP is linear is decidable in polynomial time if the MEC decomposition of the VASS is tree-like. I'm not going to explain what this means, but this is a kind of technical condition which can be checked efficiently. And furthermore, we have the same kind of gap as before. That is, if the termination complexity is not linear, then it is at least quadratic. So how is this proven? I mean, this looks very similar like the result for the non-deterministic case. So To some extent, we can reuse the ideas, only that in this case, we have to replace the role of these increments, so the effects of simple cycles with something else, with a different set of vectors. So what we do, we take a given VASS MDP, we consider all counterless strategies, that is very simple strategies, which basically select only one outgoing edge in every control state and fix this transition forever. And as soon as we do that, we obtain a finite state Markov chain. We identify bottom strongly connected components, and for each bottom strongly connected component, which is an ergodic Markov chain, we compute the long-run average change in the counter-spread transition, or the mean payoff, if you wish. There are only finitely many such vectors, and they play pretty much the same roles as these increments before. So we can use the same kind of analysis as before, only that these vectors are no longer increments. These are the vectors of expected counter changes by transitions in these bottom strongly connected components. And otherwise, our classification is pretty much the same. Also, the trick with constructing this snake, this zigzag, also works, only that now this zigzag does not correspond to a real computation. It is a zigzag or a snake consisting of vectors of expectations. So what we need to prove is that if you run the VASS, then this have a tendency to follow this snake on average. So with a sufficiently large probability, you will not deviate from this snake too much. To prove the associated bounds is a nice exercise in Martinger theory and in using Azuma's inequality. Fortunately, we had a very good PhD student on board who could perform all of these nasty computations. So this is the way how we were able to prove the result mentioned in here. Okay, the last bit concerns the model of VASS games. So if we have so here we have only non-deterministic states again, but the non-determinism is solved in two ways. So these circles are demonic states where the decision is made by a player who wants to prolong the computation as much as it can, while this diamond corresponds to an angelic player who wants to shorten the computation. So now we have like an interplay between two players. One of them wishes to non-terminate and the other wishes to terminate. So again, we can define for every configuration a termination value, which is defined by this equality. So fortunately, the games we are considering here are determined. So this equality holds. So intuitively, this termination value of a given configuration is the length of the path obtained if both players, angel and demon, play optimally. And again, we can define the termination complexity as a function which to every n assigns the maximum termination value of a configuration where all counters are bounded by the n. So what are the existing results? Well, again, there are not too many. So the first result says that for every k, the problem whether the termination complexity of a given VASS game belongs to the class GK is NP complete. And we also have a kind of gap saying that if this L does not belong to GK, then it grows at least as fast as the function fk plus 1, so the generator of the next class. So in the proof, we heavily rely on the fact that this GK class is closed under function composition. So the proof technique cannot be reused for proving the same result for the polynomial hierarchy. Because, I mean, if you take the class of quadratic functions, they are not closed under composition, right? If you compose two quadratic functions, you do not get a quadratic function. So this proof technique does not work. And this is not just a coincidence. We were able to show that the problem of whether the termination complexity of a given VASS game is quadratic is actually p-space hard. Again, we have some recent results indicating that this might be optimal. So we currently believe that the problem is actually p-space complete. And this holds not just for 2, but for every k, which is at least 2. So that will be it. To the best of my knowledge, there is nothing more known at the moment. So what are the directions for future work, for future research? Well, of course, there are many, many open problems, especially for these stochastic and game theoretic extensions of VASS. And it will be really interesting to know what can be done, because so far most of these results are encouraging in the sense that you can do things efficiently. So I believe that by establishing further results, we might establish some basis for techniques applicable to the analysis of probabilistic programs. So I would be also interested to know to what extent are these results actually useful in the analysis of probabilistic programs. So this is all I had to say. So thanks a lot. And Pavel, I think it's your turn.
Thanks very much. I guess people are allowed to unmute themselves. So if everyone could please unmute themselves. And yes, let's give Tony a round of applause. And we have a question from Nir Peterman. Please go ahead, Nir.
I was actually clapping. That's not a question.
Okay.
Oh, sorry. Oh, I thought that was a hand. I misread the icon. I do apologize. Okay, so we'll take questions. David Mestel, please go ahead.
Hi, thanks for the talk. So I had a question about, so another model you could imagine, especially for example, if you were wanting to more directly model your first example, is one where the transitions have some priority, and a low priority transition is only enabled if a higher priority transition, if no higher priority transition is enabled. I just wondered, do you know anything about that?
A short answer is I don't. A longer answer is that it is known that if you try to extend the expressive power of VASS or Petri nets with some innocent looking concepts, you may very easily get undecidability. So I cannot answer the question for the model you have in mind, but I would not be surprised if there were some undecidability or at least untractability result.
That's what I thought might be the case. Although I guess it's almost, but not quite, contained in the MDP model, where you give like the high priority thing weighting 1,000,000. Anyway, thanks.
Yeah, this is interesting. Yes, thanks.
Any further questions? Okay, I've got a question. I mean, it's not directly related to termination complexity, but I haven't seen these VASS MDPs and VASS stochastic games before. I was wondering where these definitions came from. I mean, they both obviously look supernatural, but I mean, for example, these stochastic games where you have sort of one player that tries to prolong the computation, another player that tries to shorten this computation. Is that? I mean, where is this? What's the kind of origin of these sorts of models? And what are they used for?
So, I mean, there is a classical paper which classifies the type of non-determinism in computer programs, and there are these, I think, like 4 notions of non-determinism, and the angelic and demonic non-determinism is really an important concept, meaning that the demonic non-determinism is the one generated by the environment of the program, and the angelic non-determinism is the non-determinism which can solve the system by itself. So the model I have shown you with this angelic and demonic control states is just basically an instance of this general design principle. So yeah, that's the only, that's it.
Okay, thank you. And I guess these, I mean, I'm sorry to keep coming back to Petri nets, but I guess these VASS MDPs will be very closely related to stochastic Petri nets, right?
Well, in stochastic Petri nets, as far as I know, this is a fully stochastic model, right? So you don't have a non-deterministic choice in there. Basically, the semantics of a stochastic Petri net is a continuous time Markov chain usually.
Right. Well, I think there's a few different ways of getting semantics, but yeah.
So how exactly are these two models related to, well, I don't know at the moment. Yeah.
Okay, thanks. Great. Are there any further questions? Okay, in that case, let's give Tony one more round of applause and we can end the recording. So thanks again.
Thanks a lot.